The next topic we're going to look at is the notion of geometric predicates. So this is a very powerful concept that's going to be useful later on. In particular, when it comes to lots of geometric algorithms, we typically deal with geometric objects that I introduced in the previous video as essentially abstract objects. Then we have a particular geometric predicates that deal with the formulation that we've used in the past. So most of the geometric formulas and the math formulas go inside the predicates, and then most of the rest of the algorithms that we're going to be implementing don't really have that much math into it. So let me explain. So let's say we have a point and we have a line. One of the typical examples or typical operations or decisions that we need to take in many geometric algorithms is to know whether the point is above the line, on the line, or below the line. Okay, this is known as sidedness test. This is used in many different algorithms. So how do we do sidedness tests? So depending on how you implemented the line, or how you represented the line, and how you represented a point, the formula, though, the math that you need to use to decide whether point is above or below is different. In this particular case, when the representation of is simple and the representation point is just x and y coordinates, this is quite simple, right? So if you look at this point, the x coordinate on the line that is on the line, then you have its x coordinate x and its y coordinate ax plus b, just because of the formula of the line. And now if the y coordinate of a point is bigger than this, then the point is above. If it's equal, it's on, and if it's smaller, then it's below. Okay, so the sidedness test can be represented something like this. And the interesting point about the sidedness test is that this math can just go inside a function. So you can have a predicate, so you can have a function that does the sidedness test, and then it has as a parameter, it has a point and a line. So it has a point P comma line L, and then it would return essentially above, below, or on, and all the math goes inside here. And depending on how you represent the point, you could have, let's say, different functions that kind of, let's say in C you overloaded or whatever. That or if you do object-oriented programming, you use the whatever software engineering principles that you want. But essentially the point is that all this math only goes inside here. This math comes here. And the rest of your program can only deal with essentially the abstract object of points and lines. Because for most geometric algorithms, you're not really interested in how exactly you model the point. A point is a point, and the concept doesn't really change how you have modeled it. And if you have basic geometric predicates can answer questions like this, then the rest of your algorithm is essentially independent of how you have chosen to model a point. That's a very powerful concept. So let's move on. Try to pause the video to think about this question. What if the line is given as ax plus by? The final question is, this is a little bit harder, is that what if the line L is given by 2 points P1 and P2? In other words, it's not this formulation that you're given, but it's given by 2 points. So you have a point P1 and P2 that uniquely defined line. If you look this up on the internet, you can get a formula like this. That is a determinant of this matrix. You can look at the determinant of this matrix, and depending on the side of this determinant, you can know whether this is above or below. But it's actually not necessarily true. What this does actually gives you a sidedness test. In other words, you have point P1, P2, and P3. Let me erase this. So 1, 2, 3. This will tell you whether when you go from P1, P2, P2, and then you P3, whether you're doing a left turn or a right turn. The sign is going to be positive in one of the direction. I don't exactly remember in which direction it's going to be positive, but we can quickly check. But the important thing here is that this is known to be the signed area of a triangle. In other words, if you make a triangle with these 3 points, this formula is actually the area of this triangle. If this area is 0, this means that points 1, 2, and 3 are on the same line. But the area could be positive and negative depending on which direction you turn. So you can have this situation when you're turning this way, or you could have this situation 1, 2, 3. Right, if you go from 1 to 2 and from 2 to 3, then you're turning to the right. So I think in this formulation, if you this way is positive and this way is negative, I guess we can check that if you set x1 to be the origin, which means that x1 and y1s are 0, and x2 is 1 and y2 is 0. So you put 0, 0, and 1 here. And if we put 1 here, then the sign of y3 is going to be, so this is going to be eliminated, and this is just going to be y3, and x3 is 1, and these two are 0. So essentially, if y3 is positive, so this is going to be positive, which means that we have a left turn. So left turn is positive, a right turn is negative.